And we have, I think we only have 8 lectures left, so 7 plus exam, so almost 6 left. My gosh. Is that so? We have 7 lectures left. So we're at the end. Let me open my little scribble. It goes by very quickly. It's amazing. Okay. Pa, pa, pa. Okay, so what we're going to do first is we're going to go over another example. So last time we stopped at, we did one example last time when we had to use solver because we had expressed we had expressed our stoichiometric table in terms of extent of reaction. So you should start getting used to this idea to use extent of reactions to express your stoichiometric table because it will become very useful. We could have solved this problem similarly using concentrations, but because it was gas phase, it would have been a bit more difficult to do it that way. So we decided to do it only in terms of extent of reaction. So we stopped there, and I hope that that you guys don't have any questions on that. So what we'll do today is another set of examples. Let's see if I can find them. Okay. Yeah, so the first example we'll do is actually semi-batch. There's one in the book, but we'll do one here using concentrations. Yes, we'll do it using concentrations as the variable for the stoichiometric table. And we'll be using as well Python, and I will share with that. Oh, give me a second, guys. Oh. I hope that you guys play with Python. I will share a link of a Python tutorial of how to solve ODE, differential equations in Python. So I will share that on Canvas. So you can go and learn more of how I wrote some things. So you can, there's a cool little website that does that. Okay, let me see. Okay, so let's look at another example of multiple reactions. So we have, in fact, already done examples of reactions in series because they're not different. The way to solve them is kind of similar to reactions in parallel in terms of method, but in the notes last time we sort of covered reactions in series, how to plot CB as a function of CA. So we did some of that. So let's look at another example, and this is examples of reactions in series, or examples of multiple reactions. By the way, there is a very high chance that there will be a take-home portion for exam 3 that requires that you use Python. So basically that take-home portion will be assigned pretty much like a day before the actual exam, so you have time to do it. And you'll post that part separately. I'm designing the exam in a way that you use that information to continue some of the exam problems, but that could be difficult to do. But I will try. So let's see, example, semi-batch. And the statement is that there are two reactions. So we're doing two reactions, but we can do 3 or 4. It just becomes more complicated to derive all the rates. And this is isothermal, liquid phase, batch reactor. One thing you'll notice generally is that liquid phase reactions are ran in batch reactors. It's not often that you see gas phase reactions in batch reactors. So we have a parallel reaction. So we have A to B goes to D, and B also reacts to form E. And now the first reaction minus RA is 0.5 times CaCb squared, and R minus RB here in the second reaction is 0.25 Cp squared. I hope that's correct. Okay, so this is a semi-batch, and what you're at, and what is happening is it says that initially reactor contains 5,000 liters and Ca naught is 5 mole per liter, and Cb naught, oh, actually no, let's say Ca naught is 1. Did I change it? I changed it. Ca naught is 1 mole per liter, and Cb naught is 10. But we'll change it later. We can change it if we want. Okay, so mole per liter, and at time t0, so when the reaction starts, A is fed at a concentration of 2 mole per liter. And a volumetric flow rate of 1,000 liters per hour. So every hour, the volume of the reactor goes up by 1,000 liters. So the question you ask is to calculate the selectivity of E with respect to D after 4 hours. So that looks a little daunting, but it's actually not. It's actually not daunting at all. So the way you go about in this problem is we can in fact start with the mole balance as we usually do, but we'll do a mole balance on a batch reactor, which we did before briefly, but we'll do it once again. So let's do a mole balance on A. So if you do mole balance on A, we can do the same: in minus out plus generation equals accumulation. So it's a semi-batch reactor. So what we out is 0 because nothing's coming out, but in we do have Fa coming in. And generation is RAV, and accumulation is dNAdt, right? So that's our mole balance there. Now, Ca is volumetric flow rate of a feed. We'll call that V feed. This is that 1,000 liter per hour here. This is the V. This is the feed times Ca feed. And that's plus RAV. And that's equal to dNAdt, which is dCAV dt. And that is Ca dV dt plus V dCA dt. Because the volume is changing, so it's a product rule of the derivative. So now we can, let's see, we can, oh, did we have a question? No. Let me check something really quickly. To find the easiest way to go about it. Mm-hmm. Oh, this is acting out again. Make sure. Yeah, I made a mistake somewhere. I have a mistake somewhere. This is, so let's just rewrite it so we can be sure. That's the mistake. This is just CA. Yeah, that was a mistake. That was not what confused me for a second. I don't know why I wrote feed on both, but anyway, so if we divide through, so the first thing we need to know is what dV/dt is. So if you do a mass balance, and we derived this before, you find that dV/dt is equal to the volumetric flow rate being fed, right? So if you do that, then you have yeah. Okay, so you can then rearrange. You can divide by V. So this is the concentration of A. Let me check. Oh yeah, that's right. That's actually right. See, that was once again completely messed up here. Yeah, this is CA fed. That's right. Yeah. So if you divide by V, you get dCA dt plus what? What has happened here? Yep, so you can solve for dCA dt is RA minus this over V. So that's what the mole balance on A looks like. Sorry, I got confused for a second because I was going back and forth between.
Shouldn't that be plus? Shouldn't be RA plus V
Yes.
feed?
Yeah, that's right. So Yeah, so that's your mole balance on CA. So that's what we're gonna, these are the ones we need to derive. So we can also do a mole balance on B. So we do a mole balance on B. It's again, we do the same. So here, in fact, there's no B being going in or out. So we just end up with RBV equals D NB dt. And this is CB dV dt plus V dCB dt. So we can solve once again for DC, you can solve for dCB dt. And that's going to give you RB minus it's going to give you this. So if you do the mole balance on D or E, it's going to look the same as B because they're not being, fed or removed. So on D, it's going to look that way. And on E, it's also going to look the same. Okay, so we've done the mole balances. Now everything is in terms of concentration. So that, and you'll see in a moment that actually makes things quite easy for Python for us to solve. So we also have our initial conditions. So our initial condition is at time 0. We have CA is some CA naught. I believe that's 1 mole per liter. And CB naught is 10 mole per liter. So that's what we have initially at time 0. And we have no D or E. So these are the things we need before we go into any sort of solving software. So these are the things we need to derive. We need to derive the mole balances, but because we're dealing with concentration, there is not really a point to do a stoichiometric table. Now, the one thing to keep in mind, however, is that this reaction is all 1-to-1. So if we go back, it's all 1-to-1. So if you have to relate the rates. So if, for example, you had 2D, so that would be 2 times minus RA, right? So we'd have to relate the rates. So you should keep that in mind. So we didn't need to do any of it. Okay. So you can, once you write all the rates and you use the stoichiometric relationships to get the rates to relate, then we can go into Python and I can show you what that looks like. Where are we? There we go. Can you guys see this? I hope.
Can you zoom in a bit?
Say that again.
Can you zoom in a bit?
In this page? Yes. Let's see if we can. That's better?
Yeah, that's much better.
Yeah, okay. So I'm gonna post these. So this is just Jupyter Notebook, but I'm gonna post the Python file itself so we can see. So we usually import NumPy as NP. We just give it a name as NP. And from NumPy, we import the integration, OD integration. So this is a SciPy integrate that we call it ODent. We're importing ODent. And we also import the plotting module, matplotlib pyplot as PLT. This is the problem statement I just worked out. And now this is the solution here. So I define a function. I just call it semi-batch2. And I give it 2 variables, Z and T. Now Z, if you're familiar with Python, you can have indices, right? So you have Z0, Z1, Z2, Z3. So Z0 is A, CA, Z1 is CB, Z2 is CD, and Z3 is CE. So I put in some of the variables in the problem, right? So you've got our V feed. I didn't call it V feed for some reason, but that's what it stands for. This is V feed. K1, K2, the volume of the initial volume of the reaction, and this is the concentration at which Ca is being fed. So here I put in the differential equation. So this is dCA dt. It's V times Ca feed minus Ca. So this is Z0. This is what's changing, divided by V minus K1 Ca Cb squared. So Z0 is Ca and Z1 is Cb. So that's the rate, Cb squared. I input all four. So dB dt is this equation here. One thing about B is that it's being used in both. Oh, did I actually write RB? Oh, I didn't write out RB was. I should have done that. So here, RA, so RA is only K1 CACB squared. RB, the net rate for RB is being consumed in both reactions. So it is minus K1 CACB squared minus K2 CB squared. Okay, so it's being consumed in both reactions. For D, it's only being made in the first reaction, so it's plus K1 CACB squared with the same minus V CD over V plus K1 CACB squared, and E is minus V CE over V plus, in this case, is 3 K2 CB squared. So these are the ODEs, and I ask it to return a DAT, DADT, DBDT, DT, and DEDT. So these are, I'll post the link in the after class to there's a nice website that basically explains what these mean. You also give a range of solutions. So you're saying you want to solve this differential equation, just couple the ODEs, and you use this NP-arrange. There is another form that's called np.linscape, but NP-arrange, the first is the start, the end, and the interval. So it starts at time 0, goes to 10 times 10, so 10 hours, and it takes 0.1 every point. It solves it every 0.1 hour. So Z naught is your initial condition. So you put those in brackets. So you have one initial conditions are concentrations, right? At time 0, 1 mole per liter of A, 10 mole per liter of B, 0 of C, 0 of D, 0 of E. And this is the actual solver. Okay, this is the solver. So I just call it concentration. Is ODEN of the function using the initial conditions respect to time. So this is actually the only function that you put in after you've defined your function. You use ODEN to solve for it. In order to plot it, we go through and now define certain things. Concentration of A is the first index. So this is what this means. So it's concentration of, in brackets, colon 0. So this is first index. This is Ca. This is equivalent to this, but outside of the function. So this is integrated. This is solved for. And Cb is the second index, C3 is the third, Cd is the third, and Ce is the fourth index. And you can also define the selectivity of E with respect to D, which is concentration of E divided by concentration of D times 3, because that's the stoichiometric coefficient that you need to take into account. So right here, you need to take those into account. And the reason I added this very, very small number is because at time 0, there is no D, so you'll be dividing by 0, selectivity would be infinity. So I added a very small number, 0.0001, to account, to keep the function from not basically diverging. One thing to keep in mind here, it should in fact be molar flow, a number of moles, not molar flow, so be number of moles, but at every point here, they have the same, the volume is the same, right? If you are doing selectivity of E with respect to D, you'd have to take into account how much, if you are doing E with respect to A, I mean, you would have to take into account how much A was already in the reactor in terms of moles. So you have to multiply by volume. So in the book, I think example 7.5, like in example 7.5, in part B, it really does that, right? It actually takes into account the number of moles that it takes into account the volumes, because it does it with respect to a reactant. So if you're doing it with respect to A or B, you'd say number of moles formed of E, which would take into account the volume. So that after 4 hours, so you'd say, okay, after 4 hours, this is 9,000 liters volume of the reactor. And then that would be, and then you'd have concentration of B that was at the beginning minus concentration of B that had been fed, or plus B that's fed minus B reacted. So you'd have to do all of that. And that's an example 7.5. So you can look that up.
Why is the numerator and denominator different?
For this,
Yeah, why did you like multiply by 3 and does it add 0.00?
yeah, so two reasons. This is the stoichiometric relationship. Remember stoichiometry, the selectivity, we said it was moles of E divided by moles of D, and then you have to factor in the stoichiometric coefficients, which basically for every mole of D, you make 3 moles of E. Right?
In our notes, we have just B goes to E.
B goes to I see. Okay, well that's what happened. I just didn't relate them, so it was B goes to 3E.
Okay.
That's what I had in the problem. So where's my pen? I'll correct that once I get back. It's B goes to 3E.
Why does that make a difference if you're just tracking the number of you're tracking concentration, not number of moles formed, right?
Yeah.
All right, and then why do you what do you do? Add 0.000?
Yeah, I added this very small number because at time equals 0, you're dividing by 0.
Okay.
Because there is no D in the. This is a thing to keep Python from crashing. That's essentially what we're doing. If you don't do it that way, Python's gonna crash. It's gonna tell you that you cannot solve for it, or it's gonna give you an error. Where's my pen? I should do that. Yeah. So in the problem, it should be B goes to 3E. So for every D that is formed, you form 3E. So that's the relationship between the two. So I put that in there to remind you all that for when you calculate selectivity, the stoichiometric coefficient should be taken into account. Just keeping in mind. Okay, so if you were doing number of moles, it would have been taken into account already, right? It would have been. So let's say if you calculated the number of moles of A, B, C, D, it would already have taken into account the 3. All right, so anyway, yeah, so then you can do the plotting. So this is time, concentration of A, which I made all of these here, put it in red and give it a line width of 2, B, same thing, and E. Put some labels in X and Y labels. And I wanted to say print the concentration of C at 4 hours this is a function that can find Y as a function of X. This is an interpolation. So NP, so NP interp, what I'm asking, it says at 4 hours of T, find concentration of E. I guess that's what I meant. Yeah. Concentration of E at 4 hours is this guy, mole per liter. Just a way of writing it. And then also print the selectivity from E with respect to D at 4 hours is this function evaluated at 4 hours, because this function also changes over time, right? So if we plot this, we find, first of all, it says that the concentration of C, I guess it's supposed to be C. Let me rerun it. So we're gonna rerun. Okay. Concentration of E at 4 hours is 9.7 mole per liter. So I guess this is here, right? You can see the plot. So in cyan, you have concentration of E goes up, but it goes down. The reason it goes down actually is because I'll explain in a moment. The concentration is going down. So, and you have concentration of A depletes, it depletes completely at 4 hours. Then you have the concentration of B, which is in blue. Oh, B is in blue. B depletes completely, right? A depletes, but it starts replenishing because you keep adding A. So you're adding A. The reason why A is going up eventually is because B is basically going down. So B is depleting, so A is going up a little bit. So at this point, there's pretty much no more reaction happening because there is no more B. Because if you look here, you need B for both reactions. So there's no more reaction happening, but there is flow. There's flow of A, so A is going up. So because there's flow of A is going up, it's actually decreasing the concentration of E, and also decreasing the concentration of D. So you can see at that point, I guess pretty early at this point, there's no more reaction happening. It's pretty low. So you start getting less and less reaction. The concentrations of the products are actually lowering because there's no more reaction. You're just adding. So but I'm thinking though, if you were to add more B, if you start with more B, let's say if we do 20 mole per liter of B, which is ridiculously high, but let's see. So did the selectivity go up? Yeah. So that's an indication that the concentration of E is higher. So your selectivity went up. So there is the problem in your, there is a homework problem that is essentially very similar to this. And you can play around with it. You can refer to this, and I don't think there's any errors there. I'll double check because I wrote it last night. There may be, so I'll check if there are any errors in there, and I'll communicate with you if there are, because there can be. And we'll go over that. Are there any questions about this?
So this file will be uploaded and we can
Yes.
refer to it for our homework.
This file will be uploaded so that you don't have to go through the pain of learning it from scratch. That would
Thank
be,
you.
yeah, that's definitely something that I don't recommend. For example, I taught myself Python maybe 2 or 3 years ago, and I still remember how long it took me maybe last week to realize that I could use np.interpolation. I don't know why it took me so long to figure that out. Because what I was doing before was very lame. I was actually, since you're counting every 0.1, at 4 hours, it's the 40th point. So you could basically look at the 40th point on the graph. There's a way to do that. And that's what I was doing. And that felt very stupid to do that way. But realizing that you could just use this and then to get Y from X made so much more sense. So yeah, so the semi-batch is it's pretty cool. So you can play around. I think the homework problem, and I'm not sure. I don't remember if the homework problem has any sort of asking you to mess around with things to increase selectivity, how you would do it. But that could be exam related. Like if, for example, how we change the feed from 10 to 20, the initial B from 10 to 20, we can increase selectivity that way. Because the main thing is that the reason why this works is because if E is what we want, right? If E is what we want, and with to slow down the formation of D, we basically we're feeding A. Well, the reverse could be happening, where in this case you'd have to feed B. If D is what you want, you'd have to be feeding B. Okay, so that's sort of the approach to increase selectivity, and these come from some of your by dividing the selectivity, the rate equations, so you could get these numbers. Okay, now this is again another parallel reaction, but one reaction that we haven't looked at a lot, or mixed series parallel. So this is an example of a mixed series parallel gas phase reaction. Yeah, so mixed series gas phase reaction. I'm gonna go back to my notes to work out all of these things, and before we put them in, to show you how this one works. So let's go back to sharing my notes. I'm gonna come back to the notes, and we'll do a mixed parallel. And after this example, we'll do a wrap up of, essentially the wrap up will talk about what's the process like. Is there a question? I did, I think. Yeah, so then I think it's here, it's gonna be 3RD, 3RB. Yeah, that would solve it. Okay, so mixed series parallel. And there's something happening all the time with my screen. The only thing missing from this example is a pressure drop. So that's the most complicated things could get, like in terms of conceptually. The only thing missing here is that we don't include a pressure drop. So once again, we're gonna do something simple here where we have a mixed parallel reaction. So in terms of A, this is a parallel reaction. In terms of C, it's a series reaction. Right, so that takes place in a PFR. It's gas phase. But instead of giving you pressures, I'm just gonna give you molar flow rates to simplify things. Okay, I'll give molar flow rates to simplify some things. Oh, I think I had it reversed. So it's 10 moles per second, and then 5 mole per second of B. So I had it that way. And the volume of the reactor is 300 liters. And you're given K1 is 0.1. And this is gonna be 0.1 liter per mole second. And before I forget, yeah, these are elementary reactions. So keeping it simple. So you have K1, which is 0.1, and K2 is 0.05. Yep. Okay, you're given those, and your volumetric flow rate inlet is 10 liters per second. Typically for those gas phase reaction, you'll be given some partial pressures and some mole fractions, and you can always get those from using the ideal gas law once you're done putting things like arranging your reactions and simplifying your mole balance and everything. So you can always do that. There's no pressure change. So like I said, the more complicated thing could be when you have a pressure change. So you'd have to put, P, small p, and put a dP dW. And in this particular reaction, there is a decrease in number of moles from inlet to outlet. So you also cannot just use P equals 1 minus alpha W to the power of 1/2. So you have to come up, you'd have to have another form of it. So yeah. Okay, so what you're asked here is the yield of C with respect to A. So but you could be asked many different things. You could be asked the number of moles of, you can be at the mole fractions at the exit. You could be asked a bunch of things. Now we're gonna set up this problem in terms of extent of reaction, because what makes it nice that way is that we have two reactions. So we have two extent of reactions. It's easier to solve in terms of that because you'll just have two ODEs. But if you do it in terms of concentration, you have 4 concentrations, but it's gas phase, so you have to take into account the volumes, the volumetric flow rates. So that makes it complicated to solve. So if we do this problem in terms of extent of reaction, it's easier because we can just do d eta 1 dV, d eta 2 dV. So let me show you what that entails. So we can start from a mole balance, which is dF I dV equals Ri, right? That's a general mole balance. So we can look at our stoichiometric table. So we have our components and what's in and what comes out. So we have FA naught, FB naught, 0 and 0. So A participates in both reactions. So it's A minus eta 1 minus eta 2. So this is FB naught minus eta 1. And C is eta 1 minus eta 2 because C is in both reactions, and D is eta 2. So you can once again look at your total flow. We call that FT naught, which is FA naught plus FB naught. And if you add everything up here, it's equal to FT naught minus E eta 1 minus eta 2. So this is your total molar flow rate out. You can also, then you have to calculate V, right? So you have to calculate your volumetric flow rate out, which is V naught.
How come on this problem you knew to make a straight cable and have the extents, but you didn't have to do that for the problem above?
You could have. I'm just making the choice for ease of solve to easy solutions, or showing you different ways you can solve, right? That's the choice I made. So initially I just said, well, you could do it in terms of concentrations. Yeah. You could do everything in terms of concentration, but you'd have 4 differential equations. So in the problem before, you could have done the same. You could have done it in terms of extent of reactions the same way. You could have done it, you'd have 2. But I just decided to do it in terms of concentrations to just show you that diversity. So you can do it in terms of concentration, but you could do the same problem in terms of eta 1 and eta 2 as well. That it shouldn't be that different. Does that answer your question?
Yep.
Yeah. So you could do it in any way. It's just a matter of choice and what you're most comfortable with as well. Helps. Let me see. Okay, so and then we don't have any temperature change and we don't have any pressure change, so we're good there. So we have our V, so we know that CA, because DF, so now let's go back to our mole balance for a second. We can do mole balance. Let's do it on, let's see. Could we do it on, I skipped something and I need to make sure that I don't make a mistake in telling you. What I did, I can tell you what I ended up with, but I need to make sure I didn't skip steps. So let me see what I did there. What did I end up with? I ended up with doing it with, so I'll write out what I ended up with. I'm sure it's right, but I skipped some steps and I can't remember which of the components I did the mole balance on. But I wrote, just give me a moment here, make sure I didn't. So A and B both goes down and C goes up and down and D goes up, which is what I expect. Okay, let me make sure. Hopefully I'll clarify this once I have a moment. So in a second. Yeah, I'm gonna clarify it, and when you come back, I'll correct myself if I made a mistake. So we have V. We can write the R1, which is the first rate, is K1 CACB, right? Because I'm saying it's elementary, so it's K1 FA FB over V squared. Right, so we can put FA and FB over V squared, so we have everything we need there. You can write R2 is K2 CA, what is it, CACC to FA FC again over V squared, and we can replace FA and FC right here. What I ended up writing in, which is correct, but I don't know, I have to think how I got there to not mislead you. I ended up writing these two mole balances. Which is correct, but that might be the first time you ever see it written that way, which I mean, I need to make sure I don't mislead you. Okay. So this is from doing a mole balance. I think the second one is on D. That will give you the D eta 2 dV equals R2. But the first one, I do wonder if that's correct, but I'll correct myself over the break if I made a mistake. So if there is any potential mistake, it could be here, but I'll fix it in a moment. So now we have, so these are the things we have. We have our mole balances. In terms of eta, we have V, volumetric flow rate. So what we're doing here, we don't need to put them, and we have our rate laws. Okay, what we're doing here, we don't need to combine them. We just have them solved for. And then we're going to input them in Python exactly that way. So that's the advantage here. Once you set up your problem, and then you have your initial conditions, you can just you can put things exactly as is in Python, and it will solve the problem for you. So let us now look at what the solution looks like. Okay, so this is just the problem statement. Now I define reaction, extent of reaction respect to volume. So these are the two terms. And I plug in my variables K1, K2, FA naught, FB naught, V naught. And I also define an FT naught, which is FA naught plus FB naught. And this is V, right? V is FT over FT naught times V naught. So FT is FT naught minus eta 1 minus eta 2 over FT naught. R1 is K1 CA, or FA, FB, right, divided by V squared. And then R2 is K2 CA CC, which is eta 1 minus eta 2 divided by V squared. Okay. So yeah, I hear say, oh, that doesn't matter anymore. I had a different definition. Okay. So these are the two differential equations. I will double check this one in a moment if that's correct. And to return D1 dV, D2 dV. Okay, so that gives no errors. That's good. And now I'm using linspace instead of np.lrange. So I just use something different. So here it tells you it starts from volume of 0, goes to 400. Remember, we're looking at 300, but I made it go to 400 just to see the plot. And this I'm just telling it to use 1,000 data points. So the difference between arange and linspace is that in linspace, you tell it to how many data points to use, and in arange you tell it what interval to use. So that's that. The initial conditions are that eta 1 and eta 2 are both 0 at V equals 0. So at the beginning of the reactor, there is no conversion at all. And then this is the solver. So you solve that reaction with the initial conditions with respect to V. So we can run this one too. And we define some things. So extent of reaction 1 is the solution of the first index, so E naught. Extent of reaction 2 is the solution for the second index, which is 1. The way that Python works is the first index is a 0 index. It's a 0, and that's the first one. So you get that. Yield with Y with respect to yield of C with respect to A, that was asked, is how much C is made, which is eta 1 minus eta 2 divided by initial concentration of A, which is 10 initial number of moles of A, which is 10 moles per second. So 10 mole per second. So that's why I made a mistake. That should be 10 and this should be 5. Okay. So yeah, and then you can also calculate FA, FB, right? FC and FD. This is from stoichiometry. This is a stoic table, essentially. And they can do the plot the same way. You can plot, here I'm plotting FA, FB, FC, and FD just to show you how they, what they look like over the reactor volume, and labeling the X and Y axes and putting some legends. So this is the plotting. Right, so if you run this guy, you find that, well, this is what's going on. So this is FB starting at 5 mole per liter per second, sorry, 5 mole per second, and goes down to almost 0, if not 0. FA starts at 10 mole per second, and again, goes down. FC basically goes up and then goes down a little bit, but then FD just keeps climbing. So you could imagine, so yeah, because basically once B is depleted, right? Once B is depleted, there's no more C being formed, but C is going to react to form D. So that's what's happening here. So once B is depleted, you basically start climbing. D starts being made, but C is now being depleted. So that's what this plot is looking like. And the question of what the yield looks like, let's see. Why did it not? Oh, I know what's happening. Oops. Let's see if that works. Yeah, okay. So you can plot the yield of C respect to A as a function of the, as you go through the reactor. And you can see that it maxes out along the same time where C stops being made, it starts going down. The yield with respect to A starts going down. And you can actually do an interpolation at 300, and it tells you that it's about 0.16. The yield is about 0.16 of C with respect to A. Yeah, so that's sort of how you can use Python to solve these problems. If I find it best to solve differential equations with Python, but you could also solve some of the things that we did in Solver also with Python. But since Excel is more accessible to most of you, it's probably easier that I showed Excel. So any questions? Yeah, I need to verify this. I'm curious how I just decided to come up with it. Okay, if there are no questions, I'm going to go back and sort of summarize multiple reactions, what we actually did, because we are actually closing this part of the chapter, although it's very exciting, but it's essentially uses a lot of software to solve things. So we can summarize this before we move on to the final exciting topic of the course, which is energy balances. After which you will become a reactor designer for sure, we hope. So we can sort of summarize what we've learned here over the last 2.5 lectures when we deal with multiple reactions. Make sure you ask questions about this, because your homework should cover all of the different kind of ways you can go about solving them, but make sure you ask questions there. And I really hope that you guys come to office hours next week to ask about homework, because it's actually probably one of the more difficult homeworks that have been assigned. So the one thing that we can summarize from here is very important things, that when multiple reactions are occurring, using fractional conversion, say XA, if A is the reactant, to solve is often ill-advised. And for two reasons. The first reason is that it doesn't tell you, say if you had a reaction where, if you have a reaction like this, you can size, so here, you can size a reactor using XA, right? You can do that. You can say for 80% conversion of A, this is what the reactor is going to look like, but you cannot calculate selectivity. So, that's out of the question, right? And if you have a reaction where you have something more like that, can't use conversion for C at all. You cannot use XC because XC is not a reactant, is both a reactant and a product, so you cannot use XC. So that's why it's ill-advised. So you have to use extent of reaction or concentration. Now, the choice between using one or the other depends on a couple of things. So using concentrations, if you have liquid phase reactions, that's pretty simple because it's constant density. It's pretty straightforward. You can use concentrations. You can use a form of the design equation that is only concentration. So you can do that. That's one of the reasons, like with the approach. So with the semi-batch, we use concentration because it's a liquid phase. We can simplify the mole balance. So to use ADA, I guess I want to say use if gas phase. You can also use concentration if gas phase. That's not really a problem, but it's preferable if you use ADA. Then you can use ADA to calculate all the moles, the number of moles coming out. So as we did in this example, where we calculated F, A, B, C, and D using the extent of reactions. That's easier to do in the back end than to do things directly in terms of flow rates. So if you use you can also use flow rates. So molar flow rates. So you could basically keep it this way. So say you have, so you can basically keep your equation that way, right? So in this case, you can say you can look at the Stoic table. So if you're doing only flow rates, which we haven't really covered because we never really use it, but you could do flow rates, whereas you have A, B, C, and D, you can just keep it that way. I guess this is 0. You can do it directly in terms of flow rates. It's not a problem. But if you do it directly in terms of flow rates, you have to write a differential equation for each component, right? So you have to do it for each component if you keep it in flow rates, because you have basically each of them becomes an unknown. You can do that as well. For the same way you do you put the concentrations in, you can do the same. You can plug these in Python the same way. In this case, your V is again Ft over Ft naught times V naught, but your Ft is essentially Fa plus Fb plus Fc plus Fd over Fa naught plus Fb naught, right? So you can plug these in. This will work too because you have 4 differential equations and you have those 4 variables, so it's still going to work the same. And you can give it a try. It's not a problem at all. So okay, so now we've talked a little bit about how we solve the problems, right? You can make choices. You can use extent of reaction if you have gas phase. You can use extent of reaction for anything actually, but using concentration is better for liquid phase. For gas phase, it's harder to do because the volumetric fluid is changing. And you can use molar flow rates for gas phase reactions quite easily. All right, so and then lastly, the one thing I wanted to add, So yeah, we should take a break in a minute. I should be finished here. One thing I wanted to add here is another trick. If you're thinking of how you do it, if you're thinking of like an algorithm, like how do you do it? The first thing you do, you can number your reactions if they have not been numbered. So if you have, let's say, 5 reactions. So you number a reaction. Second things you do, you write the mole balances. Now 1A is, well, I guess it's 3, is to choose your basis. Do you want to do eta, Fi, Ci? Which one? Well, but often you cannot use X. So you have to choose one of those. And then you have to do rate laws. You have to write the rate laws. So net rate laws. So basically that, however many reactions this occurs, and relate with stoichiometry. So that is a good relationship with your basis. So you can, that will work itself out. And then once you have all those relationships, you plug them in. In this case, if you're using Python, you plug them in, and then you write out your function, and that should be pretty straightforward. I don't. Once you do a couple of them, you'll see that it's not bad at all. Yeah, and then you can combine in Python. So you don't need to combine them by hand. Combine in Python. Okay, and the final, yeah, that's I think that's it. And now this is one side of some of the problems we solve. The other kind of problem we solved, where we're doing integration or doing calculation directly with the selectivity that we compute by relating the rates. These are time independent or space-time independent. So these are the other kind of problems we looked at. And we also looked at some qualitative aspects of how do you design a reactor, what choices you make. And I pointed you to, I think, chapter 8 on the website of Fogler to sort of practice those to get more familiar with these concepts, because they don't necessarily exist in the book that you have been assigned for the class. Okay, let's take a short break. Feel free to ask some questions before we move on to energy balances. So we hope to derive the energy balance equation before the end of class. All right, now we're gonna come back and we're going to now talk about the second to last topic in the course, which is heat effects. So energy balance. Ooh, what has happened here? Heat effects in reactions. Now, there are 3 types of reactor operations. You can do isothermal, which we basically have done for 3 months. You can look at adiabatic. Adiabatic, meaning that you're not adding heat, you're not removing heat. So whatever heat is formed during the reaction is whatever heat is formed or taken up by the reaction is the heat that is in there. That's it, nothing's changed. It's a very preferred way to actually run exothermic reactions. So the reaction heats up and the rate goes faster because, as you'll see in a moment, the reaction rate constant, except in certain cases, special cases, the reaction rate constant goes up with temperature. And we can have adiabatic, or we can have what's the best word there? You can have heat exchange. Heat exchange can take the form of just cooling or heating, right? You just have a jacket and you run some water. You can have a feed product heat exchange. where you are taking the heat from the product and then sending it right back in the to the reactants. So the heat from the product heat up the reactants. That's usually what happens with steam cracking, some of those hydrocarbon burning. So the heat that's generated goes back to heat up the reactant. So you don't actually lose. So in this case, heat is itself a product of the reaction that you recycle the heat. So it's a recycling reactor that recycles the heat back into the beginning. So you get higher. So you don't need a separate heater to heat up your reactants. So it's cool stuff like that. Okay. Now, what are we looking at? At the very beginning of the class, we wrote this KT all CI. So we could decouple in some cases. We could decouple the temperature effects and the concentration effects of the rate. And somewhere in the middle of the course, we also saw things like this. Or we saw things like this, like some absorption equilibrium. I'll remove the C. And then that's also temperature related. So in this case, you cannot decouple them, but that's okay. So we saw these things. So we can appreciate that KT follows the Arrhenius equation. Okay. And let's say K equilibrium, for example, let's say if it's an equilibrium, with respect to concentration, follows the Van 't Hoff equation, which is the K equilibrium at some reference temperature times E to the minus delta H of reaction over RT. So you can see the temperatures start to creep up in all the different forms. So that has to be taken into account because that really changes your rate. It changes your reactor design, like a lot. For exothermic reactions, what you'll find out, operating adiabatically gives you, the conversion goes up faster than operating isothermally because the heat that you form in the reaction speeds up the reaction. For example, say if you have a batch reactor, you look at temperature, reaction is exothermic, you get a curve like that, for example. Whereas for isothermal, you get this. For if you look at time and you're looking at K, this is the rate constant, it's gonna also look something like this. Isothermal gonna look like that. And if you finally look at conversion, now this is, not to scale. Conversion is gonna look something like this. Isothermal, oh no. I'll take that back. Conversion is gonna look something like this. And isothermal could actually only look like something like that. Actually, I made a mistake. That was badly drawn. I'm going to draw it again. That would be your adiabatic, and this would be your isothermal. Yeah, it makes a very, very big difference when you run things with heat, when heat comes in. Now, how does that look up in terms of our little tower that we were building? So we always think in terms of what did we learn and what do we do? We still look at our tower. So we have mole balance, stoichiometry, rate laws. These all go perfectly fine. And then we can have, we introduce a little bit of pressure drop that can be important for packed bed reactors. Then we have heat effects. And then we combine. So if you think about this, if this gives you, and let's say if you have multiple reactions, so let's put a little bracket here and put multiple reactions. Okay, let's put a little bubble. So here's what then happens. Let's say if you have a packed bed reactor, each component, and let's say it's gas phase, okay? Each component gives you rate law, the differential equation, dFA dW equals RA, da 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 da, and then you have to put in your pressure drop. So you have a d small p dW. You see, that's why Python and other solvers become really nice, because you don't have to put everything together. You can just define what each of the differential equations look like. So you have that, and then you also have dt dW. That's another one. You have 1, 2, and then you have all of these. And yeah, so you have these sets of changes now. And you have to plug them all in and then plot. Usually the best thing is to look at the profile, how they change over a certain length. And once again, you know, the temperature change, the temperature equation, so this is for packed bed reactor, will change depending on what form of operation. So if you operate isothermally, it's the simplest one. But to operate isothermally, you have to add some level of heat or remove heat. And that can be very, very expensive if the delta H of reaction is very high. So if your heat of reaction is very high, you have to remove that much heat. That becomes nearly impossible to do. And that's sometimes not economical because you have to use a larger reactor. So you have to remove more heat from a larger reactor. So it's not the best form of operation. Okay. Now, we know that, of course, most, if not all, reaction absorb heat or generate heat. Maybe not so much enzymatic ones compared to catalytic ones. The reaction rates, as you can see, vary very strongly with temperature. So when you write your, you know, you're gonna have to put in this in your mole balance, right? And yeah, these are the two things really. So what are we gonna do in this chapter? So chapter 8 in your book does a very, very, very good job, except for one thing, and we will cover it at the end of this. So it does a very good job, and I think you should also read it, pay really close attention to it. The examples in chapter 8 in the text are, I would say, not as good as the one from chapter 7, because I looked at them all. They're not as good. They're good. They could be better though. I found better ones that I will work through in class to give you a pretty good flavor. If you go on learnchemy.com, and this is the time you should go now. You should go on now. I don't think there's an E. Is there any? No, there's not. If you go on this website and you look under the modules for kinetic and reactor design, I think now I can send you there with confidence. So you can go and essentially recap or learn many wonderful things. There are little short videos, 5 or 10 minutes, looking at the multiple reactions, multiple reactors, and everything. Now I can confidently send you there. There will be some small differences with the way they solve the problems compared to what we do. But now I can tell you, hopefully you can tell the difference. And once you do, now you'll be able to understand the material even better. Once you can tell if you can understand how their solution approach is different than ours. And I think that's very well, yeah. And I would say the same thing for any other topic, you know, transport or, you know, thermal. You can go on there, and it's wonderful. So I will take some examples from there from time to time in the next 6 lectures, and I will tell you which ones I took, and I will solve them the way we solve them in the class, and I will tell you to go and look at the way they solve it, and then convince yourself that these are exactly the same, and that would allow you to understand the topic even better. That's even more pertinent for energy balance, because Roberts does a lot more fundamentals of energy balance, but these other websites and Fogler, it's more applied, and you'll be able to tell the differences. Okay, so in the next 20 minutes, we will derive the macroscopic energy balance. So we now have established that it's needed. right? We know there's benefits to it. The benefits to it are that, let's say, if you operate a PFR adiabatically or a batch reactor adiabatically, you will need a smaller reactor if the reaction is exothermic. On the other hand, if the reaction is exothermic but it's an equilibrium reaction, increasing temperature decreases your rate. But we'll get to that as well, how you can look at equilibrium reactions. So it's going to be a very, very fun topic. I would rather not cover as much in terms of external transport effects, just to spend more time on energy balances, because I think they really, really make the whole course in a wholesome, give you a very wholesome approach picture. So the energy balance goes the following. So you have rate of energy accumulation. So some of you who took thermal, maybe, well, you all took thermal, may be familiar with this now. So you have rate of energy accumulation within the system. That's equal to a rate of heat flow to the system from surroundings, right? So that's Q. So it's positive for heat going in, it's negative for heat going out. So you have your D energy of the system, dt, is equal to your Q. Sometimes I may drop the dot over the Q, so I apologize for that, but I do mean the rate of heat. I may accidentally drop it. So you have the rate of work done by the systems on the surroundings. This is your W. And then you have the rate of energy added to the system by mass flow or molar flow, I guess. You could say mass or molar flow, but I think it won't matter. And this is flow N times energy N. These are all in joules per second, by the way. I mean, they can be all in joule per second. This is basically rates of energy. Everything is in joule per second. And then that is minus the rate of energy removed from the system by mass flow. So energy leaving the system, not removed really, leaving the system. And this is your minus F out, E out. This is very, very general. We can't use this as is, of course. We have to make some changes to it. Okay, we cannot use this as that. So of course, for plug flow reactor or anything that's operating at steady state, that first term here is is 0 for steady state operation, right? And for a batch reactor, it's gonna be really like similar to dN dt. It's gonna be d energy dt. So just wanted to preambly say that. All right, so then we can take this term without having to write everything. Again, we'll take these two terms. You can rewrite these two terms as the sum of the components. So I equals 1 to n of Fi Ei in, right, minus the sum from 1 to n Fi Ei out. So that should be straightforward, to do that. The other change that we make, so the goal here is in the next 15 minutes to show how we get to the starting, not only the starting point that is in the book. So the book starts somewhere that we actually have to get there. It's not starting from something, there's something a bit more general. So we're starting from a complete energy that includes not only internal energy, but it also includes kinetic energy. It includes potential energy and other forms of energy. That's what's in this E, all the energies. But normally we're only dealing with enthalpy and internal energy, because kinetic energy and potential energy are not really that big of a factor for the reactions we're going to solve. So the other thing we make is this work is flow work plus shaft work. Okay, so this is going to be this term here, which is the work done by flow. So this is pressure times molar specific volume, specific molar volume. I think it's just what, meter cube per mole. That's the molar volume. And this is same thing out. Okay, and then plus shaft work. Now in this class, unless you're dealing with a polymer, which is a very viscous reactor, this is going to be 0 in the class most of the time. Actually, all of the time for this class, this is 0. So now we can go back to this term. We're actually dealing with, we dealt with this term a little bit. We're going to deal with this term now. And we can rewrite this equation. So let me put the units here for you guys. So this is, let's say, mole per second. This is kilogram meter divided by second square meter square. This is a Newton. And this one is molar volume, which is meter square per mole. So if you add everything together, you'll get joules per second if you multiply everything. So it is still the same units. So we can rewrite the full energy of the system as heat minus shaft work plus summation I1 goes to N F. Did I do it right or did I mess it up? No, the signs I've switched. I switched the signs. Yes, I switched the signs. Oh, maybe what I should do is this instead. Yeah, that's what I should do instead. Yeah, that's what it is, because there's a minus sign in front. Okay, got it. Okay. So the other thing to note is that EI, as I mentioned, has internal energy plus kinetic energy plus potential energy plus other things. For this class, these are 0. So the energy is the internal energy. So you can write du system dt. So that's the internal energy of the system. The other thing you know is that enthalpy is internal energy plus PVI, that's enthalpy. So FIHI is this. So we're just simplifying it. So we can write du dt is rate feet shaft work plus summation of FIHI in minus summation of FIHI out. This is the molar flow rate times the enthalpy of each species. So these are the molecular enthalpies. There you could have systems of average enthalpies, but we can say that you get, if you have a, let's say, you can take the enthalpy of formation, for example, for each of the species, and these can be given at a reference temperature. You know, we're gonna go an example of that kind of reviews thermal from that point of view, but that's kind of the idea. But most problems will give you these enthalpy values to sort of keep you from having to calculate them. But we're gonna do a short thermal review next class to calculate enthalpy and heat of reactions at different conditions based on reference numbers. So you can know that this is a thing that you need to know in case you have to use it. And for a convention, we can rewrite this as, this is our starting point. As a convention, we can rewrite this as Fi naught Hi naught minus sum of FIHI. So this is where we start with an energy balance. Okay. So this is, I believe at this point, is closer to equation 8.1 in the book. Closer, not exactly there, but it's closer to that. Okay. Now what we'll do in the next few minutes is just do a couple more simplifications so we can get to an energy balance that we can actually use in problems. So this follows the book quite closely. So the book has this written this way, but before I write this, I think I should first define. If you remember your chapter 1, we go back to that. This is your extent of reaction. This is your extent of reaction for multiple reactions. So this is your definition for multiple reactions, meaning if you have reaction K, in reaction K, you have species I, and then the extent of reaction for reaction K. So this is essentially that. So if you have one reaction, it's Fi minus Fi naught equals mu I E1, eta 1. So this is your extent of reaction from basically chapter 1 or 2. So you can write as the book actually has it to make it simpler to follow. So you can basically write this as and Fi comes from the extent of reaction calculation. 1 to R. So this is reaction R. Okay. So this is And these are, instead of, the book has it as partial molar enthalpies, but you can replace it with pure component enthalpies because of, you assume everything is well mixed. So at least the components are well mixed. You don't have partial molar enthalpies. So you can write this in terms of pure component enthalpies. So you can rearrange this to have oops. This is eta k and summation of I from 1 to n of mu ki hi. So this is where it gets really cool, because this term here is actually the heat of reaction at the temperature T. So that's what this term is. So yeah, so this term is the heat of reaction at temperature T. And this term right there, right, is actually you can get it by doing molar heat capacities dt. So you can integrate molar heat capacities. So hi naught minus hi is from T to T naught, molar heat capacities times dt, or if you have an average molar heat capacity that doesn't change with temperature, which is often what we're gonna have, of that doesn't have temperature, we can actually calculate it as T naught minus T. We can basically have it outside of the integral because it's an average molar heat capacity. So that leads us to the actual equation for, this is the energy balance that we are going to further simplify for different systems. So let's say you have a single reaction, single reactor, batch reactor, CSTR. The one thing that will be a little tricky that we're going to introduce later is when we have tubular reactors with heat exchange, where the heat will, the temperature needs to be integrated over the length of the reactor. So we're gonna have a dt dw instead of just T minus T naught. So here, that T minus T naught term here, we can't really just do that for a plug flow reactor or a packed bed reactor where the temperature is changing as we go through. So we can't really do that, but we'll get to that when we get there, and I will show, and I will make sure, because the book in Roberts does not treat that. So if you look, it does not treat plug flow reactors in that way. It doesn't integrate over the length. So if you look in the examples in the back, it actually does not really have plug flow reactors and packed bed reactors with heat exchange. So that's what we're going to introduce at the end, so you can have a complete picture. It's not actually complicated much. So in any case, so this is the energy balance, at least when we have an average molar heat capacity. Oh, there's a reaction K here. Make sure I didn't forget. So for PFR and of CSTR and steady state stuff, you'll see that this is 0, right? For in the class, shaft work is often 0. For PFR, CSTR is steady state, DOS, DT is 0. And for example, for an adiabatic system, Q is equal to 0. You're not adding heat, you're not removing heat. So you can see how this energy balance can become more and more simple. And before we finish, one quick thing I wanted to add is those two terms. This is well discussed in the book as well. And this is the two terms delta H. So the HI naught, so the H in minus H out term that we looked at up here, it became two terms, right? It became this term and that term. So what this term is how much heat you add or remove. So that what that is the rate at which heat is added or removed to bring temperature of inlet to outlet temperature. So that is that. So you're breaking down, so essentially what you're doing is you're breaking down your process into two kinds of heating. So you have a heat of that you're somewhat adding to bring your temperature up. And you also have the heat of reaction itself. So this is the rate of enthalpy change associated with conversion. So these are the two things, and that's going to become important because you can think of it as heat generated and heat added. So when you think of it that way, that's going to become important for all of our analysis of CSTR, analysis of PFRs, analysis of batch reactors, how much heat you're adding versus how much heat is the reaction making, or how much heat is the reaction taking up, and how much heat you're actually removing. So you have these sorts of analyses. Now, to quickly summarize what we are actually going to do in this chapter before we go. So what we did just now, before deriving this, we kind of spoke a little bit of length about why running an isothermal reactor may not be ideal, because you actually could get better yield and better conversion if you run adiabatic. You should always consider adiabatic in reactor sizing because it could give you a smaller reactor, as we will see. And then in the next course, in the next lecture and beyond, we're going to look at sizing and analyzing those reactors. But we're going to do batch reactors at different operation: adiabatic, heat removal, and as well as we can also look at isothermal to calculate how much heat you would need to remove for the reactor to be isothermal. So that's also important. And you would see how much heat you need to remove for some reactors. It's not practical. But by the end of this chapter, the nice thing we're going to do, and you should all get excited about it, really, is that this concept of multiple steady states. So depending on what temperature your reactor is, the reaction may not start. And at some point, so you have multiple steady states. You could have a steady state where the reaction does not start. You can have a steady state where the reaction is at 95% conversion because of the temperature. And you can have issues where if you start increasing the temperature, the reaction suddenly goes from 0% conversion to 90% conversion and blows up because of the heat that's generated as a result of high conversion in exothermic. So we're going to look at all of these things, and we're also going to look at equilibrium as a function of temperature, so that you can see that if you run a reaction, a reversible reaction, that reaction may, you have to remove heat from it. If an exothermic reaction, you have to remove heat from it to be able to get equilibrium to keep going. And we're going to introduce something that is not in the book that's called reactor staging, where you go from in between reactors, you drop temperature so you can increase conversion. So this is multiple reactor staging. That's the concept of that. That's something quite useful to keep reactions going forward that are in equilibrium. Okay, so that's all I've got. I know we passed 4:55, which we usually do, so I'm sorry. And I will see you guys next Tuesday. And I think what happens next? Nothing happens, right? The quiz has been pushed back. Okay, yeah. So I'll see you guys next Tuesday. And yeah, nice to see you all.